Okay, before starting this derivation, torque experienced by current carrying loop, let's revise two formulas which we did. First one was, if there is a current carrying wire placed in a magnetic field, it experiences a force which is given by F is equal to BIL sin theta. This theta is between I and L, right? No, it is IL cross B. This was the formula. So that means the theta, the angle is between the conductor length and the magnetic field direction. Second formula was, when a wire or a conductor, current carrying conductor, has this current flowing through it, then the magnetic field due to this wire will be in this shape, right? It will be vertically outwards from here and vertically inwards on this side. If I place another wire in the magnetic field of this conductor, so this conductor is also going to experience some force. Then we did another formula for this, which was force per unit length. That is, force experienced per unit length of this wire is given by mu naught upon 4 pi I1 I2 over R, right? This were the two expressions which we did. Now let us start the torque experienced by current carrying loop placed in a uniform magnetic field. What will happen if the magnetic field is non-uniform? Right now we are talking about the uniform magnetic field. So for torque there are two equal and opposite forces, but in case it is non-uniform magnetic field, there will be torque, but there will be some sort of translatory motion as well. We have already discussed this in electrostats. In uniform electric and magnetic field, there is a simple torque and a simple rotational motion, but in case of non-uniform electric or magnetic field, there is rotational as well as translational motion, right? So I have this diagram like this. This is my field magnet, north polarity and south polarity. Then magnetic field is in this direction. I have a current carrying loop like this. This loop is having current flowing in this direction, that means anti-clockwise direction. If the loop is straight like this, then you can see the current is like this, but right now due to the torque or due to the force experienced by the sides of this loop, the loop is already rotating in motion. That's why you are seeing a tilted motion of this. In this way the loop is rotating. How did I figure it out that the loop is rotating this way? See, apply Fleming's left hand rule and the direction of force experienced by the wire. See this part. Let us name this A, B, C and D. In part AB, current is, what is force field current? Force field current, right? So in part AB, current is in this direction and force field, sorry, this is field. Field is north to south and the current is flowing in this direction. So that means force is vertically outwards. This part is coming vertically outwards and this part is going vertically inwards. It's like this. Suppose this is my loop, the rectangular loop of wire. So it will be rotating in this direction, right? This is how, this is the outcome of the overall torque. For torque, see, how do we do this expression? Before explaining torque, let's find out force on wire AB and CD. Force on wire AB is BIL, right? Guys, if you are confused about the fact that the formula was not BIL, actually it was BIL sin theta C. I would rather do it for you. You guys need not to write this. Just understand the formula was IL cross B, right? If I expand this, I'll get ILB sine of theta, where theta is the angle between L and B. Where theta here, length is like this, magnetic field is like this. Now, no matter what, how this wire is going to rotate, this wire is always going to make an angle of 90 degree with the magnetic field. So theta is always going to be 90 degree. So ILB sin 90, and due to which it will be ILV. So that is why I wrote straight away BIL. So you can write the whole or you can write only this much. both are okay and acceptable. Now, FAB is BIL, which is equal to force on the wire CD, right? The only difference is the force on AB is in this direction, whereas the force on CD is in vertically inwards, that is opposite direction. So these two forces are actually equal and opposite in direction or anti-parallel in direction, separated by some distance. So this thing constitutes a couple. What is a couple? Two equal and anti-parallel forces. And then the moment of force. What is moment of any physical quantity? That physical quantity multiplied by the distance or the line of action or the perpendicular distance. So the moment of force, that is torque, is given by either of force. You have to either of force into perpendicular distance. Now what I was saying, you have to write the statements here. What are the statements? That since the loop is under the action of two equal and anti-parallel forces, the net result is the torque, and torque is given by what? Either of force into perpendicular distance, right? Okay, I'll start from this point again, but now you need to focus on what about the lines AD and BC. These are also current carrying conductors, but are there not any forces acting on them? For example, let's say this wire, okay, this AD was in this position initially. After that it is rotating like this, and there will be some part or some time at which the position of AD will be like this and again like this. Alright, let's just find the angle between what? L and B in case it is like this and this. Okay, magnetic field, when the conductor is in this direction, length and magnetic field are in the same direction. That means the theta will be 0 degree and BIL sin 0 will be 0, and ultimately there will be no force acting on AD, and hence there will be no force acting on BC. But when the wire is in this direction and magnetic field is in this direction, getting my point? Magnetic field as it is in this direction, and the wire which has taken the complete turn like this. Initially my loop was like this. After rotating 90 degree, this part which is AD is making an angle of 90 degree with the magnetic field. Now in this case, if I apply the formula BIL sin theta, I will get BIL. So why I am not considering the force on AD and BC? Because these two forces, see the direction, BIL sin theta, what is force field current? Let's find out force field current. Magnetic field is in this direction and current is going in this direction, like vertically inwards. So it's like this, right? It will be easier for me to show it like force field is in this direction and current is in this direction, like this. Okay, force field current, right? Now if I apply the same formula on what? Right now the force is vertically downwards on the wire AD, hence on the complete loop ABCD. But if I apply the same formula on the wire BC, which is like this, and magnetic field is like this, I will get the force is in vertically upward direction. So hence these two forces will nullify each other. So you can also add this statement that force on wires or the current elements BC and AD cancel out each other. So the net forces acting on wires are FAB and CD, which are equal and anti-parallel in direction, hence they constitute a couple, and the moment of force is given by torque, which is either of force into perpendicular distance. Now to understand this, what are the forces and what is the perpendicular distance, you will have to see this diagram from upwards, like from this position here. You will have to stand on top of the board, and you will be watching it like this. See, so just try to imagine that this whole diagram is tilted like this towards your side. Okay, so the diagram would be somewhat like this. Let me make the length. This is length L and this is breadth B. So here I have already utilized the L part, which was the length of the conductor. Now when you will see it from the topmost position, it will be something like this. The wire will be like this and the forces are acting like this. Magnetic field is in this direction. So what is the perpendicular distance between these forces? Perpendicular distance would be this part, and theta is what? Theta is here, hence this will be theta. This is force 1 or FAB, and this is force 2, which is FCD. So considering this diagram, I have to find the perpendicular distance. So I'll be using sine theta. This is my x and this is my breadth b. So sine theta is perpendicular upon hypotenuse, which is x upon b. That means x is equal to b sine theta. This would be the diagram if you see this part from above. Alright. So continue this line, either of force, that is BIL into the perpendicular distance, which is x, and change x with what? B sine theta into B sine theta. This part L into B is what? Length into breadth of this rectangular loop. That means this is the area. So you have BIA sine theta, and this is the actual answer of torque. But what if there are n number of turns? Now I am going to damage this diagram. If there are n number of loops in this part, so the torque will be multiplied by n times, and hence the total formula for n number of loops becomes n BIA sine of theta. Guys, note it down. This is your final answer for torque experience on current carrying loop.